So first of all, let me remind you what we have done so far in this course. If you remember, we started our discussion by recalling the basic order of operations. We then defined term and polynomials. And then we raised a very interesting question. If two or more polynomials are given, can we add, subtract, multiply, and divide two or more polynomials? Answer to this question was yes. In fact, addition, subtraction, and multiplication of two or more polynomial is really a simple task, right? We realize that division of two polynomial requires a knowledge of factorization. So we recall the idea of factorization. This factorization is done in three stages. Remember, look for the greatest common factor. If there is none, then think about factoring given polynomial, given trinomial using that spatial method, the factorization of trinomial of the form ax square plus bx plus c technique, right? If that doesn't work, then we look into the spatial factorization formula. Using one of these three methods, we factorize the given polynomial. If none of these three technique works, then we simply conclude that given polynomial is non-factorizable, right? With the help of factorization, we were able to divide polynomial by polynomial. And if you remember, we were talking about how to deal with rational expression in the last lecture. I showed you series of examples multiplying, dividing polynomials as well as adding, subtracting polynomials. I would like to start today's lecture with those two sub-problems that we couldn't do in the last lecture. All right. And once we are done with these sub-problems, I will try to give you brief idea about how to solve linear, quadratic, and rational equations. All right. We will try to understand difference between expressions and equations. So for the very first time, I am using the word equation. All right, and we will learn how to deal with equation carefully. All right, so this is the problem that I would like to discuss first. If you notice, the first and second problem, they are the two sub problems from last Thursday's uh, lecture handout, right? I'm going to show you this problem on the board. I will write them side by side and I'll explain you how they are connected to each other. All right. So let's try to solve these three sub problems on the board, and then we will get into the idea of equations. All right. So,
Professor,
is,
what lecture notes is that lecture 2 that you're referring to?
yes, from lecture 2, right?
Okay.
We were unable to solve fourth sub problem of the first problem and fourth sub problem of the second problem.
Okay, right. Thank you.
Right. Mhm. So here are those two problems. So the first one is asking us to add two rational numbers, 3 by 4 and 5 by 6. Right, and the second sub problem asks us to, add two rational expressions involving polynomials. X over x square minus 1 plus 2x plus 1 over x square minus x minus 2. All right. Let's carefully try to recall how we handle this addition. Pretty sure that most of you know how to add these two numbers. I just wanted to recall the strategy carefully. All right. We know for sure that in order to add two rational expression or two rational numbers, we must find the common denominator. How do we find the common denominator? Well, in order to find the common denominator, I will have to find out the least common multiple of these two numbers. All right. Let's try to recall how we calculate the least common multiple. In short, I am going to write LCM to represent least common multiple. This is going to be our common denominator. All right. In order to find common denominator or least common multiple of these two entries, I am going to factorize them completely. All right, so I'm going to factorize 4 first. We know that factorization of 4 is really 2 into 2. I would factorize that 6 as well, and its factorization would be 2 times 3. All right, so once you factorize both numbers in the denominator, I want you guys to calculate the least common multiple of these two numbers. In order to compute that least common multiple, this is all you need to do. Find out if there is a factor that shows up in the factorization of both terms. All right, if there is a factor that is a common to both numbers, you would count that number only once towards least common multiple. All right, so for example, 2 is one factor that shows up in the factorization of 4 as well as in the factorization of 6. So I would count that factor only once. And then I go ahead and include the remaining factor. I have one more copy of 2 that's coming from the factorization of the first denominator. And then I have a copy of 3 that's coming from the factorization of that second denominator. All right. 2 times 2 times 3 is going to be the least common multiple. All right, and we know that this really equals to 12. So 12 is the least common multiple of these two numbers. All right, so 4 and 6, they have least common multiple 12. So my goal is very clear. Make 12 visible under this term and under this term. I want 12 in the denominator of the first term, 12 in the denominator of the second term. In order to do that, I'm going to multiply and divide the first term by that missing factor 3. Right? I want 2 times 2 times 3 in both denominators. Here I have, in the second term, I have 2 and 3 visible in the bottom. What's missing is one more copy of 2, so I would multiply and divide it by 2. Want you to notice that the denominator is equal under both terms, right? So I'm going to write it as a common denominator. Let's do that. Look, 2 times 2 times 3 is going to be the common denominator. In the top, I have 3 times 3 plus 5 times 2. All right. So again, once the denominator is the same, we can perform this operation on the expression sitting in the top. Now, deliberately, I am using word expressions. All right. This expression could be numbers or could be polynomials. All right. Very soon, you will see the connection between both of this example. Well, I would like to simplify. I would like to apply this operation on the expression in the top, but that in order to perform that operation, I must multiply these entries. Well, we already know how to multiply numbers, right? 3 times 3 is 9, 5 times 2 is 10, and then this is divided by, now that we only have one denominator, feel free to multiply them, write it as 12, and then we really perform this operation. We end up getting 19 over 20. Again, I know that all of you perhaps are aware of this technique. I just wanted to remind you that idea so that you can connect this idea with what we are going to do now. Now remember, this example is really created by replacing those 3, 4, 5, and 6 by polynomials of various degree. All right, again, I replace those 3, 4, 5, and 6 by different polynomials to construct this example. All right, I'm going to repeat the same idea here. All right, what we need to do, we need to come up with the least common multiple of the terms sitting in the denominator. So my first goal is to factorize this denominator and that denominator. We know how to factorize them, right? Let's try to factorize both of these denominators so that we can calculate the least common multiple. Let's start with x square minus 1. Looks like this is two-term expression in form of difference of two squares, right? Looks like a square minus b square. Do we know its factorization? Answer should be yes. Its factorization should be a minus b, a plus b. Meaning, in this case, the factorization would be x minus 1, x plus 1. Right? This is a full factorization of denominator of the first term. Let's factorize the denominator of the second term. X squared minus x minus 2. I want you to notice that there is no common factor in these three terms. This is a trinomial of the form ax squared plus bx plus c. So I must try that trinomial factorization method that we learned in the last lecture, right? The leading coefficient is 1, constant term is negative 2. Product of 1 and negative 2 is going to be negative 2. Now the question is this: do we know any factors of negative 2 whose sum is negative 1? If answer is yes, then I can factorize it. If answer is no, then that means I have to look into spatial factorization formula. All right. So let's check. The only factors of negative 2 are negative 1 and 2 or negative 2 and 1. Right? The sum of these two factor is 1. Sum of these two factor is negative 1. You see, that's what I was looking for. So I found out the factors of AC that adds up to B. Now here is the next question. Can I write down the factorization directly? Answer should be yes. Why? Because this polynomial is a monic polynomial. Leading coefficient is 1. So I can write down the factorization directly. What will be the factorization? X minus 2, x plus 1. Right? So this is the factorization of the denominator of the second term. All right. Let me write down what is the least common multiple. Let me write one step here. Let me, replace those denominator by their factorization. Just to make it look like the first problem. Look, we are exactly moving in the same direction. 3 divided by factorization of 4, so x divided by factorization of x square minus 1, and then 2x plus 1 divided by factorization of x square minus x minus 2. All right. Okay, time to make the denominator equal in both terms so that we can perform addition on the expression in the top, right? For that, I must find out the least common multiple or the common denominator, if you want to call it common denominator. How do we find least common multiple? Well, we do the same trick. We check all the factors. If there is a factor that shows up in the factorization of 2 or more, denominators, then we count that factor only once towards least common multiple. So x plus 1 will be counted only once. Then I have x minus 1 and x minus 2. So I'm going to keep those two factors. This is the least common multiple, or if you want to call it common denominator. All right. This is what I want in the denominator of each of these terms in order to add expressions in the top. Let's make it visible. All right. So look, I have x over x minus 1, x plus 1. What's missing from this product is x minus 2. So I'm going to multiply and divide it by x minus 2. All right. The entire least common multiple is visible under the first term. Under the second term, we can make it visible too. So I have 2x plus 1 over x minus 2 times x plus 1. The missing factor is x minus 1, right? So I'm going to multiply and divide it by x minus 1. All right, perfect. Denominator is the same under both terms. I'm going to write it as a common denominator now. Look, the common denominator is x minus 1, x plus 1, x minus 2. In the top, I have x times x minus 2 plus 2x plus 1 times x minus 1. All right. Now think about it for a second. In order to perform that addition operation, I must multiply this two polynomial and I must multiply this two polynomial. We had the same situation in the previous example too. In order to add these two expression, I must multiply those two numbers, right? The question is, do we know how to multiply two polynomials? Answer should be yes, right? To multiply first two polynomial, you have to use distributive property. To multiply these two, you simply need to FOIL it out, right? Let's do that. I really get x squared minus 2x plus 2x squared minus 2x plus x minus 1 divided by x minus 1, x plus 1, x minus 2. Collect the like terms and simplify further. X squared plus 2x squared, they adds up to 3x squared. Negative 2x plus x, they adds up to negative 3x. And then I have minus 1. And then this is divided by x minus 1, x plus 1, x minus 2. Now let me make one very interesting comment here, right? In this particular example, I end up getting 19 over 20. 19 over 12, sorry. All right. It's clear that no further division is possible. The top and the bottom, they don't share the common factor. For example, if I would have gotten 4 over 6, then I could have crossed out 2 from top and the bottom and I could have rewritten my final answer as 2 over 3, right? We would like to make sure that that's not happening here as well, okay? If it is happening, then you need to cross out the repeating factor from the top and the bottom to reduce it further. Understand, it was not the case here. All right, is it the case here? Let's check. All I have to do is check if this trinomial can be factored further. And if it is factorizable, then factorize it and see if there is a cancellation between factors in the top and the bottom. That's all we need to check. All right. So let's check it. Look, this is a non-monic polynomial. Product of A and C is negative 3. The only factors of negative 3 are negative 1 times 3 or negative 3 times 1. What do we want for factorization? We want factors of -3 whose sum is -3. Is it possible? Check. Sum of these two factors is 2. Sum of these two factors is -2. There is no way that we can come up with factors of -3 and their sum is -3 as well. Meaning this trinomial is a non-factorizable trinomial. Meaning we cannot simplify this any further, and that is really the end of the story, right? Now, as I say, look at these two examples side by side. What I would like to say here is these two examples, they are replica of each other. There is no real difference between any of them. Logically, they are exactly the same. The only difference is here I have used numbers. Here I have used polynomials. Still, the process remains the same. All right. Okay, let's try to see with one more example if we can apply this process on a particular example or not. So we have this third sub-problem in today's lecture note. In problem 1, third sub-problem has this expression. I have x over x plus 1 plus 2 over x minus 1 minus 3 over x square minus 1. All right, I would like to add 3 rational expressions. We play the same game, right? I would like to find out the least common multiple of all 3 denominators. In order to get that least common multiple, I will have to factorize all 3 denominators. So let's check carefully. X plus 1, this is a linear term already. X minus 1, this is a linear term as well. No further factorization is needed. All right. This term, x squared minus 1, this is the only term that can be factored as x minus 1, x plus 1. So let's try to, replace that denominator with its factorization first. I get x over x plus 1 plus 2 over x minus 1 minus 3 over x minus 1 x plus 1. Let's write down what is the least common multiple of all 3 denominators. Again, we are going to do the same thing. For least common multiple of 3 denominators, I will check one by one each factor. X plus 1, it repeats in the factorization of 2 terms. So x plus 1 should be counted only once towards least common multiple. Same deal with x minus 1 too. Look, x minus 1 repeats in factorization of 2 denominators. So I must count it once as well. Least common multiple will be x plus 1 times x minus 1. This is what I want in the denominator of every single term to perform this addition and subtraction operations. Let's make it happen. The first term is missing x minus 1. So I will multiply and divide it by x minus 1. The second term has x plus 1 missing in the denominator. Right? So I'll multiply and divide it by x plus 1. The third term has both x minus 1 and x plus 1. So no treatment is needed on the third term. So third term stays as is because it has got both factors in the denominator. Now denominator is equal under all three terms. I'm gonna write it as a common denominator. Let's do that. So I have x minus 1, x plus 1. That's our common denominator. In the top I have x times x minus 1, 2 times x plus 1 plus 3. In order to perform this, sorry, there was minus sign here. In order to perform these two operations, I will have to, use the distributive property here. Let's do that. Get x square minus x plus 2x plus 2 minus 3 over x minus 1, x plus 1. If you simplify like terms, you get x square plus x minus 1. We would like to check if there is further simplification possible. Okay. Check if you can factorize this trinomial any further. Do we know any factors of -1 whose sum is +1? The factors of -1 and 1 are going to be -1 times 1. And their addition is really 0. There is no way that you get factors of -1 with sum +1. All right, meaning no further factorization is possible for this trinomial. This is really the end of the story. So that's really final simplification of that three-term rational expressions. So as I said, there is no trick in adding, subtracting rational expression. It uses the same logic, right? Find out the least common multiple or common denominator, and once you have common denominator with you, make it visible under every single term and then simplify the expression in the top, right? So this is the idea that we need to implement every time we add or subtract rational expression. Now, as I said in today's lecture, I would like to give you a brief idea. I would like to recall the information about linear equation, quadratic equation, and if we have time, then I will also go over rational equations. All right. So before we get into this idea, I want to make the difference between these two terms clear. Expression and equation, these are two different things, right? Expression is the word that I have been using from the very first lecture. By now, it will be very, very clear in your mind that expressions can be simplified. All right, so expressions can be simplified, right? You can simplify expression by, adding like terms, or by, using distributive property, or by multiplying polynomials and things like that, right? Equations are different, all right? Equations are basically used to express that two expressions are equal. All right, so again, here is the definition of equation. Equations are used to represent that two expressions are equal. So you have some mathematical expressions here, and you have mathematical expression on the other side as well, and you are saying that these two expressions are equal. All right, if that is the case, then what you get as this entire thing is called equation. So remember, there is an easy way to identify equation. It must have, comparison signs involved in it, right? When I say comparison sign, what sort of comparison signs you guys have seen in the past? Equal to, less than equal to, greater than equal to, less than or greater than, right? So again, we will keep the things as simple as possible. Equations are used to represent two expressions are equal. As I mentioned, difference between equation and expression should be clear before we get into the next idea. Expression can only be simplified, all right? And this is something that we can do by adding, subtracting like terms or using factorization. Things that we just did, right? Equations can be solved for the given variable. All right, so the major difference is this: expression can be simplified only. There is no equal to sign in the expression. Equation has equal to sign, so you can solve equation for the variable x or whatever variable is given. All right, we would like to start by discussing the simplest type of equation, linear equation. All right, so as I said, we would like to discuss three things depending on the available time: linear equation, quadratic equation, and then if we have time, then I will go through, rational equation as well. Okay, so let's start with the linear equation. First, definition. Okay, the equation of the form ax plus b equal to c with a different than 0 is called linear equation. All right. You should always ask a question that what is this condition for? What happen if a is 0? All right. If a is 0, then that would make a times x term 0. And you really have b equal to c. You are simply saying two numbers are equal. This is no longer linear equation. When I say linear equation, it is linear in the variable. The highest power of variable is going to be 1 for linear equation. All right, so the highest power of the variable needs to be 1 for linear equation. All right, so understand that a different from 0 is the necessary condition to make this definition a sense, right? So any equation that is in the form ax plus b equal to c with leading coefficient different than 0 is going to be called linear equation. All right, sometime you may need to simplify like terms or shift the terms from left side to right side to make it look like ax plus b equal to c. All right, so you may have to do some algebra to convert given equation into this standard form. All right, the question is how to solve it. Again, I'm going to give you the general strategy, step-by-step strategy first, and once we have general idea clear, we will try to implement it on the set of problems. All right. So let's talk about how to solve this in general. Okay. So as I said, equations can be solved for the variable, right? In this general form, the variable is x. If you want to solve this equation for variable x, you need to isolate x. And this isolation must be done logically, right? So using the proper logic, we are going to isolate variable x. How do we to isolate variable x? I need to get rid of this b and a, all right? And I'm going to get rid of them in a logical way. All right, remember the order of operation, you have to go in the reverse way. Addition, subtraction must be removed first, and then multiplication, division should be removed next. Okay, so look, what I'm going to do is I will try to get rid of that b first. And how do we get rid of b? I would say add negative b on both sides of this equation. All right, add negative b on both sides of this equation. That will remove b from the left side and it will send that b on the right side. Okay, the equation, the form of the equation that you are going to will look like this: ax equal to c minus b. All right, so we got rid of one number. Now to get rid of that a, divide both sides by a. All right. So divide both sides by a and you will get x equal to c minus b over a, and that is really the solution of our linear equation. Pretty simple, no? So as I said, you guys should have seen this in the past. My goal is just to recall this because we will be using this idea so heavily in this course. And trust me, if you feel comfortable with this basic review material, then you will not struggle in this course. This course will be straightforward and simple course if you are strong algebraically. All right. So as I said, now that we have general strategy, we would like to see how to solve, how to implement it on particular set of examples. In example number 2, I have 3 sub-problems for you, and I am going to solve all these 3 problems on the board. I will write them side by side, and we will use the same idea, same general idea that we just discussed, right? So let's work out these 3 problems on the board carefully. So let me clear this out first. Okay, so here is the first sub-problems of example number 2 from today's handout. We would like to solve 3x plus 6 equal to 17 for variable x. Here is the second sub-problem. 3p minus 7 equal to 11. We would like to solve this linear equation for variable p. And the third sub-problem is this equation 5 times 4x plus 5 plus 4 equal to 2 times 3x plus 7 minus 4x. All right. Okay, so notice that the first and second problem, they are in the standard form, ax plus b equal to c, right? My goal is to isolate variable x, all right? And I'm going to do it in 2 steps, 2 logical steps. Add negative 6 on both sides to get rid of this 6 from the left side, and then divide both sides by 3. Let's do this, all right? So as I say, to eliminate 6 from the left side, I would add negative 6 on both sides. Let's add negative 6 on both sides. 3x equal to 17 minus 6. Now let me mention here that I know many of you write one additional step here. They would do 3x plus 6 minus 6 equal to 17 minus 6, and then they cross 6 out. I want you guys to make a habit of not doing that. All right. Remember, it was our intention to move 6 over to the other side. And that's the reason why we are adding negative 6. We are doing it to get rid of this 6. You don't have to do this. It's perfectly fine if you just write 3x equal to 17 minus 6. No need to write plus 6 minus 6 on the left side. Make habit of this, and this will save a lot of your time. And it will also potentially eliminate some sign errors, all right, or computational errors as well. We know 17 minus 6 is going to be 11. I now need to get rid of that 3. I'm going to use the same logic. Divide both sides by 3. divide both sides by 3. Alright, if you divide both sides by 3, you are going to get x equal to 11 over 3. Again, there is no need to do the following. Divide both sides by 3, cross this 3 out, and then do 11 over 3. No need to do such thing. Alright, it was intentional move. Alright, if the generalization is clear, then it should be very clear that we wanted to send this 3 over to the other side, right? And to send it over to the other side, we have to divide both sides by 3. When you divide by 3, that 3 will be gone, its location will be changed. You don't have to, you know, cross 3 out from top and the bottom. Alright? Even you don't have to write those two statements down. This is really like a natural process. Alright? And I'm going to do that on the second problem just to show you how much work is really required. Add 7 on both sides. Alright, I get 3p equal to 18. Divide both sides by 3. If you cross out the repeating factors from the top and the bottom, you get p equal to 6. All right. So this is how much work is needed. You don't really have to write these things down. Because this was the first illustration problem, I try to include all the details. But in your mind, it should be clear that solving linear equation requires me to isolate variable. All right. To isolate variable, this is what we need to do logically. Right. Let's try the last example. As I said, you may have to use some algebra before you use the general idea. Let's try it. All right. So this is also linear equation. However, in order to solve it for x, I have to use distributive property on the left and the right side, and then I have to deal with the like terms on both sides. Let's. If you distribute 5 over both terms, you get 20x plus 25 plus 4. If you distribute 2 over both terms, I get 6x plus 14 minus 4x. All right, we need to simplify the like terms. On the left side, I have two numbers. On the right side, I have 2x to the power 1 term. We need to simplify them. Let's simplify them. I get 20x plus 29 equal to 2x plus 14. Right? There is only one variable here, and that is x. How do we solve this for x? Well, to solve it for x, I need to isolate x. All right? The problem is that I have variable x on both sides of equality. To isolate variable x, I must need all the like terms on one side. So what I want you to do next is, separate like terms by the means of equality. Meaning, move this 2x over to the left side. At the same time, move the number 29 to the right side. How should we do that? Well, add negative 2x on both sides and add negative 29 on both sides. Again, add negative 2x on both sides and add negative 29 on both sides. Remember, this is, intentional move. 20x is staying here, adding negative 2x on both sides We'll shift that 2x over to the other side, adding negative 20 on both sides. We'll shift 29 over to the right side. All right. Same operation that we have performed in the first step of both of these sub problems. You can do this on multiple terms, right? If you don't feel comfortable doing these two operations simultaneously, do it one by one. First add negative 2x and then subtract 29. You will get the same result. After two or three attempts, you will realize that this is really smooth process of shifting terms, right? 20x minus 2x, that's 18x, and 14 minus 29, that's negative 15. To solve this for x, I must divide both sides by 18. Let's do that. Divide both sides by 18. There is a common factor 3 in the top and the bottom. Cross it out. Your final answer will be negative 5 over 6. Right? So it should be clear that solving linear equation is perhaps super simple task. Right? There is no trick there. All I have to do is move the numbers from one side to other side, isolate your variable x, and once the isolation process is done, you get your solution for linear equations. So linear equation, they are pretty easy to solve. Straightforward idea, right? Next item is quadratic equation. Let's try to understand the quadratic equation and general available methods to solve them. All right, we are going to work exactly in the same way how we dealt with a linear equation. I will give you the definition of the quadratic equation first, and once we have a definition, I will talk about general methods to solve them, right? There are three methods that I am going to show you, um, and so let's try to go through the definition first. All right. The equation of the form ax square plus bx plus c equal to 0 with leading coefficient a different than 0 is called quadratic equation. All right. So again, always ask a question that why this condition is there, right? What if a is 0? If a is 0, then that would make your x square term disappear. You will have linear equation only, right? For quadratic equation, the highest power of x needs to be 2, right? That a different than 0 kind of makes sure that the x square term is there. So this is a legitimate way to define a quadratic equation. All right. So equation of the form ax square plus bx plus c equal to 0. It's called quadratic equation where a is different than 0 or leading coefficient is different than 0. I want you to notice that we have seen this left side in the last lecture. Remember the general form of the trinomial, we know the factorization technique for ax square plus bx plus c. All right, so that is one thing that I want you to keep in mind, because the methods that you are going to learn, there is one method that is going to use that idea. Remember, you may have to, shift the terms from left to the right. You may have to add, subtract like terms in order to get this standard form. So this form, I'm going to call it standard form of the quadratic equation. All right. Okay. I would like to mention here that there are three methods, three general methods that I'm going to discuss with you um, regarding this quadratic equations. However, out of these three methods, I'm going to show you how to use the first two methods. These are the two methods discussed in our textbook. The third method is also a popular method. If you read online resources, you will find out this third method. However, that third method is somewhat tedious. All right, so I'm not going to use that third method here. At least I would like to give you the general idea. But those of you who are interested in that third method, there are certain family of quadratic equation that can be solved very quickly using the third method. All right, but let's go through these three methods one by one. Starting with the first one, the one that all of you should have seen in your high school. All right, this first method is called quadratic formula. All right, so as I said, most of you must have heard this word quadratic formula. All right, let's try to recall the general outline of this quadratic formula method. In order to use this method, what I want you to do is write down the quadratic equation in the standard form. When I say standard form, I really mean the right side has to be 0. If it's not 0, make it 0 by moving all the terms on the left side. All right. And then find out what is your leading coefficient, coefficient of x to the power 1 term, and the constant term. I need these three numbers. And this method only uses these three numbers to write down the solution. All right. So we need the leading coefficient, coefficient of x to the 1 power term, and the constant term from the quadratic equation in its standard form. All right. Let me tell you how we would like to use these three numbers. Using these three numbers, I am going to create a brand new number, capital D. This is how I will create that capital D. B square minus 4AC. So square of the coefficient of x power term minus 4 times leading coefficient times constant term. I want you to calculate this number. All right, this is going to be a number because a, b, and c are numbers. So b square minus 4ac has to be a number. I have three options for this number capital D. All right, the first option is if d is positive, then we declare that there are two real solutions or two real roots of our quadratic equation. So our quadratic equation has two real roots if d is positive or b square minus 4ac is positive. The question is, what are the roots then? Well, roots can be calculated using this formula. Negative b plus square root of d over 2a. The second root will be negative b minus square root of d over 2a. All right, so it's a very simple case. If d is positive, there are two roots. Negative b plus square root d over 2a, negative b minus square root d over 2a. What if d is 0? If d is 0, then square root of d is 0 as well. If you throw d equal to 0 in this formula, you get x1 equal to negative b over 2a. You get x2 equal to negative b over 2a. What does this mean? This means that you only have one real root that repeats two times. All right, meaning there is only one real root with multiplicity 2. Multiplicity 2 means it repeats two times, right? Quadratic equation must have two roots. If these two roots, we have three choices. Two roots could be different or they could be equal, or there is no roots, right? So if d is positive, two real roots, two real and distinct roots. If d is 0, then there is only one real root of multiplicity 2, and that is negative b over 2a. If d is negative, then we conclude that there are no real roots. Some of you may have taken college algebra course where you may have seen the concept of complex numbers, right? So The roots are imaginary numbers here. As far as calculus is concerned, we don't have any place for complex or imaginary numbers. All right, so if d is negative, the process terminates right there. We would simply say that there are no real solution, and that's the end of the story, right? So this is the first method, very popular method, and as I said, most of you must have seen this method in your high school, right? It deals with the coefficients only. Find out a, b, and c, compute d. Based on the d value, you can make a comment whether or not your quadratic equation has two real distinct solutions, one repeated solution, or no real solutions. All right. Method number two. This method is called factorization method. This is the preferred way. All right. Why am I saying it's a preferred way? Because this is the fastest way to solve the quadratic equation if applicable. All right. As I said, unfortunately, this method does not work always. This method requires you to know the factorization of the trinomial ax square plus bx plus c. If we cannot factorize ax square plus bx plus c, then we cannot use this formula. All right, so this formula, this method is exceptionally fast, but it comes with this negative side effect that not all trinomials can be handled using this idea. All right, as far as this course is concerned, 99.9% of the times when you will be asked to solve quadratic equation, factorization formula will work. All right. In the second and third segment of this course, we will use this idea heavily. So I strongly encourage you guys to practice as many problems as possible for quadratic equations. All right. The idea itself is very simple. All right. Factorize the trinomial, write the equation in the standard form, make sure the right side um, in your equation is 0. Then factorize the trinomial, factorize the left side, and then set each of the factor equal to 0 and solve the corresponding linear equation, and then done. All right. So this is all we need to do in order to use the second method called factorization method. And this is our preferred way. We have the third method as well. And this third method is called completing square method. All right. Basically, let me tell you what we would like to do here. We have the trinomial on the left side, which is of the form ax square plus bx plus c. Right. So I will write it as ax square plus bx, and then I will leave some room for one mysterious entry, and then I will write down my c. All right, so this is my quadratic equation, right? Understand that this is ax square plus bx plus c equal to 0. I created two blank entries, right? Plus something minus something. This, in order to balance the equation, these two entries needs to be exactly the same entries. All right. Okay. So the question, let me tell you what I would like to do. What I would like to do here is I would like to find out this third term that makes this triple ax square plus bx plus that third term together a perfect square. All right, remember the perfect square formulas from the spatial factorization formula. If you have a square plus 2ab plus b square, we can factor it as a plus b whole square. If you have a square minus 2ab plus b square, we can factor it as a minus b the whole square. What I would like to do, my intention is very clear, that I would like to use the first two terms of the standard form ax square plus bx together with the third term that makes the triple a perfect square, so that I can factor that triplet using one of this formula, and then I would send those numbers on the other side of equation. All right. Once the factorization is done, I would solve the corresponding linear equation. The big question that we have is which which term would make the triplet a perfect square? How do we find out that mysterious term? Well, we have a formula to calculate that mysterious term. All right. This is the formula. Last term is really middle term square divided by 4 times the first term. So you square bx divided by 4 times ax square. Whatever you get is going to be the third term that makes the triplet a perfect square. Again, as I said, I have no plan to show you example using this particular method. This is the method not discussed in our textbook, but if you search online resources, you will find out this method everywhere, right? So many textbooks, they discuss this method. This is a popular method, right? Since it's not discussed in our textbook, for now, I'm not going to show you this method. Those who are interested, I can show you that method after the class. But during the class period, let's not worry about this third method, all right? As I said, I would like to show you two examples to demonstrate the first and second method. These are the two problems that I would like to solve using method number 1 as well as method number 2, and then I will let you guys compare which method to use. And then if we have time, then we will talk about rational equations. All right, so let me go to the board and show you how to solve these two sub problems from example number 4. We would like to solve quadratic equations, and we will use the quadratic formula first, and then we will use factorization method as well. And I'll keep the work side by side so that you can compare the amount of work. So here is example number 3, sub problem 1. We have x squared plus 5x equal to 24. All right. So as I said, first thing first, using quadratic formula. So this is method number 1. Using the quadratic formula. All right. I'm going to work step by step. The first step is simple. Convert this into the standard form and then figure out what are A, B, and C. All right. So let's do that. So here is the first step. To convert this into the standard form, I want right side to be 0. So add negative 24 on both sides. Again, add negative 24 on both sides to convert this quadratic equation into its standard form. Now, I want you to compare it with the standard form. Ax squared plus bx plus c equal to 0, and figure out what are the values of a, b, and c. All right, it's not difficult to identify. A is 1, b is 5, c is negative 24. All right, obviously you don't have to write down the general form. Since this is the first example, I will try to write down every single detail. You don't need to write that general form of of quadratic equation. All right. Okay. In the second example, I will skip that part. But for now, let's write it down. Using these numbers A, B, and C, I'm going to calculate capital D, which is B square minus 4AC. Again, no need to write down the formula. All right, you can do the computation directly with these numbers. Look, 5 square minus 4 times 1 times negative 24. I get 25. Product of these three numbers is 96. Looks like we get 121. Notice that D is positive. We can conclude that there are two real roots or two solutions. All right, there are two real roots for our quadratic equation. How do we find those two roots? Well, the first root is going to be negative b plus square root of d over 2a. And second root is going to be negative b minus square root of d over 2a. Obviously, we don't need to copy this formula while writing the solution. Since this is the first problem, I'm copying it down. But in your solution, it's okay if you don't write any of this formula themselves, right? Let's throw the values in. Negative of b, b is 5. Square root of d, d is 121. And 2 times a is 1. Now we know that square root of 121 is 11. All right. Negative 5 plus 11, this is 6 over 2, and 6 over 2 is just 3. So the first root or first solution is really 3. All right. Again, simple idea. There is no trick. As I said, it's a computation-based example. Pure computation. If you know the formula, then this is simple work. Use A, B, and C to calculate D. Based on the value of D, you make a conclusion how many roots are there or there are no roots. D is positive, so there are two roots. I would also like to make comment here that these examples are selected. They are created carefully, and that's why we end up getting a nice outcome for this particular number. All right. If you get something like square root of 13, leave it like that. Perfectly fine. All right. In this case, we have a nice integer square root of that particular number. This might not be the case always. All right. If that's not the case, leave that number under the square root sign. No further simplification is needed there. All right. Okay, let's compute the second solution. Negative 5 minus square root of 121 over 2 times 1. Negative 5 minus 11 over 2. Looks like that's negative 16 over 2. We simplify it as x2 equal to negative 8. So there are two solutions of this quadratic equation, and we got them both using the quadratic formula. No trick, right? So straightforward use of the formulas. All right. Method number 2, using the factorization. So here is the second method. Certainly you don't have to use both methods. You can only use one out of these two. Using factorization. All right. If you want to use factorization, you still need to write your quadratic equation in the standard form. So add negative 24 on both sides. I get x squared plus 5x minus 24. I want you to notice that this left side is a trinomial, and we know how to factorize the trinomial. We don't know yet if it's a factorizable trinomial or not. We will have to check this. All right. Okay, so this is a monic polynomial. Coefficient of x squared term is 1. Looks like I need to find the factors of negative 24 that adds up to 5. Are you aware of any factors of negative 24 whose sum is exactly 5? Well, think about it. I would write down all possible factors of 24. Negative 24, negative 1 times 24 or negative 24 times 1, negative 2 times 12 or negative 12 times 2, negative 3 times 8 or negative 8 times 3, negative 4 times 6 or negative 6 times 4. These are all possible factors of 24. Does any of them adds up to 5? Well, check. 23, negative 23, 10, negative 10, 5, negative 5. So we have one set of factors that adds up to 5. All right, negative 3 and positive 8. Can I write down the factorization directly? Answer should be yes. Why? Because this is a monic polynomial. Look, x minus 3 times x minus x plus 8 equal to 0. All right. What do we know about product of two expression being 0? Well, if product of two expression is 0, that really means one of this factor has to be 0. This is a very interesting property in algebra. It's called zero divisor property. If product of two expression is 0, then one of this expression itself, one of this factor itself has to be 0. Think about it in terms of numbers, right? If I say product of two number is 0, when can this happen? This happens only when one of those two number must be 0, right? If you take two non-zero number, their product cannot be 0. So if product of two entry is 0, then that automatically means that one of the factor needs to be 0. Want you to do that same thing here. Set the first factor equal to 0. Set the second factor equal to 0. Solve for x. This is the linear equation. So isolate x, add 3 on both sides, add negative 8 on both sides. Done. This is the solution of the given equation using factorization method. Again, this is the amount of work that you need for both methods. As I said, this method does not work all the time. If we cannot factorize the trinomial, then certainly we cannot use this method. In such case, forcefully we will have to use the quadratic formula. All right. Let's end this lecture with that second sub problem that we would like to solve using both methods. Right. So in next 3-4 minutes, we are going to, solve that second sub problem. And in the second sub problem, I am not going to copy all these formulas so that you can see the amount of work that is needed. Look, we have 4x squared equal to 4x plus 3. I'm going to write this in the standard form. So shift these two terms over to the left side. Subtract 4x from both sides. Subtract 3 from both sides. Compare it with the standard form and write down the values of a, b, and c. Looks like a is 4, b is negative 4, c is negative 3. All right. Let's calculate d. b square minus 4ac, negative 4 square minus 4 times a times c. Do this computation carefully. Negative 4 square is 16. Product of these three numbers is 48. I get 64. Since b is positive, there are two real roots. And what are they? Well, let's write them down. The first root is going to be negative of b, negative of negative 4, plus square root of d over 2 times a. A is 4. All right, again, no need to write down the formulas. Simplify this. 4 plus 8 over 8. This is 12 over 8 or 3 by 2. This is the first solution. Find out the second solution. Negative b minus square root of d over 2 times a. All right. This computation is symmetric. The only difference is the sign of that square root d term. 4 minus 8 over 8, I end up getting negative 4 over 8 or negative 1 by 2. All right. As I said, we can solve the same problem using the second method as well. Let's do that work carefully. I will write the problem in the standard form. 4x squared minus 4x minus 3 equal to 0. All right. Okay. I would like to find factors of negative 12 that adds up to negative 4. Not a difficult thing to compute. Negative 6 and positive 2. These are the two factors of negative 12 whose sum is negative 4. Here is the question. Can I write down the factorization directly? Answer should be no. Why? Because the polynomial is not monic. All right. So I will have to go through that three-term computation, three-line computation. Rewrite that middle term as a sum of two like terms based on this factorization, right? So negative 4x is rewritten as negative 6x plus 2x. Group the first two terms, group the last two terms. Take common factor out. 2x is the common factor. Leftover is 2x minus 3. Common factor is 1. 2x minus 3 is left over. Now focus on these two terms. Take the common factor out. Common factor is 2x minus 3. Let's pull it out. Left over is 2x plus 1. Now use that zero divisor property. Product of these two factors is 0 only when either your first factor is 0 or second factor is 0. All right. Solve this linear equation for x. Add 3 on both sides. Divide both sides by 2. Add negative 1 on both sides and then divide both sides by 2. Look at that. We get the same two roots. All right. So as I said, there is no trick in any of this example. So this is a good time to stop. So let's stop here. When we meet next time, I will continue from this point onward. We'll discuss how to handle rational